The next presentation is going to be given by Dana Drachsler Cohen, and it's going to be on the synthesis with abstract examples. Please.
Yes, thank you. So, hi. So, why do we need synthesis with abstract examples? So, let's start with programming by examples, or PBE. So in PBE, we have a user and we have a synthesizer, and the user provides a set of input-output examples to the synthesizer, which in turn returns a program consistent with the examples. So if you will, there's a teacher and there's a learner, and the teacher tries to convey her intent to the learner through these examples in the hope that the learner will return a program that she could use on unseen inputs. Unfortunately, with this approach, this is not guaranteed that for all input this program will behave as expected. Now let me demonstrate this behavior on a real-world PBE synthesizer. So FlashFill is a PBE integrated in Excel. Let's see what happens when Eli Gold here wants to use Excel to send personal messages to lawyers in his firm. And what Eli Gold wants to do is to send messages of the firm hi, the person's first name, come at a given meeting time. So let's see what happens. So he starts typing the first few messages, and then FlashFill kicks into action and synthesizes a program and auto-executes it on the remaining inputs. So at the first glance, it worked like charm. But if we look at it carefully, we see that actually the first word is not the greeting hi, but rather the concatenation of H followed by the second letter of the person's first name. So what went wrong here? So what we had an input space and we had a program space over some DSL. And Eli Gold provided us with two input-output examples, and then FlashFill looked for programs consistent with those examples. So it found some program, and then it executed on the remaining input, but why was it incorrect? Well, this is because that if we only look based on the examples, there are a lot of options that are not equivalent, and many of them don't capture the user's intent. And the question that we ask in this work is, can we guarantee to learn the exact user's intent? So it is probably clear that if we want to extend PBE with the notion of exact learning, we need the user to somehow validate the program. And if the validation goes successfully, then we know, yes, we have learned the user's intent. And otherwise, probably the user will have to provide some counterexample, and the PBE will look for another program, and so on. So this might look familiar to some of you, because in a way, this resembles a lot to Siggy's counterexample guided inductive synthesis, where you learn a program based on some example, and then you ask, is this the correct program? Usually you ask this a specification or some other naive implementation of a program, but based on this, you can guarantee this exactness that we want. But in fact, this actually fits into the setting of exact learning. So what is exact learning? So this was introduced by Dana Angloin in 1987. And in her model, there's again a teacher and a learner. And the teacher maybe provides some initial examples. And then the teacher and the learner interact with each other until at some point the learner says, yes, I got it. I know what you exactly want. So in Angloin model, she proposes two kinds of queries. The first kind is membership. So you can give an input-output pair and ask a teacher, is this consistent with the target program behavior? And another kind of query is the validation, where we can actually ask, is this the correct program? Namely, is this the program that you wanted to have? So you could pose this query if you have some specification, or it just so happened that the user can actually read the program. So it is probably clear that membership queries are much simpler for users, mostly if they don't know how to read programs. But on the other hand, validation enables us to converge even if the input space is infinite. And our question is, can we enjoy both worlds? So in this work, we propose a new kind of query, which we call abstract membership queries. And this kind provides a middle ground between membership and validation queries. So at a high level, an abstract membership query will partially describe some candidate program, and a set of abstract examples will enable us to describe a program on all possible inputs. Now, the crux here is, how do we represent these abstract membership queries? So what we do in this work is to focus on programs that manipulate strings. And we all know a good abstraction for strings, regular expressions. But regular expressions describe languages, and we are interested in describing functions. So what we do, we extend regular expressions to what we call sequence expressions, or SE. And what they allow us to do is to relate outputs to their inputs through verbals. So let me demonstrate to you how does abstract example would look. So here we see our first kind of verbal on the left side. This is the X0. So on capital letter means that this could represent any string. So basically what we say here is that the function is that for any input, the output would be the constant string hello, space, followed by the input that we got, X0. Now, in the second example, we see another kind of verbal, the lowercase verbal, which represents any character, that is string of length 1. And what we see here is that if we have two strings, such that the first one consists of at least one character, the output would be hello, and then the initial of the first string, a dot, a space, and then the second string. Our last kind of verbal replaces the clean star with some indication of what is the length of the star expressions. So here what we see is that for any string that starts with at least some character, and then it is followed by some number of h, the output would be b as many times as we had the case. So this is roughly how sequence expressions look like. And what we do, we call the first part the input sequence expression, the second part the output sequence expression, and altogether they are the sequence expression pair. Okay, so how can we use these abstract examples with synthesis? So as before, we have the teacher, we have the learner, and as before, the teacher provides an initial set of input-output examples. And as before, we still give it to some PBE. We are parameterized with this PBE. We don't implement it ourselves. So then the PBE will come up with some program that is consistent with the examples. But at this point, we will give it to our algorithm called LSEP, which I'll discuss in a bit. And what LSEP does is generating abstract examples that describe this P. So it generates these abstract examples, poses it to the teacher, and then the teacher can say if this is the correct behavior or not. So say that she says yes. So now maybe we have to come up with another abstract example because this hasn't covered the entire input space. And say that this time the teacher says, no, this is incorrect behavior. So she will also give us some counterexamples. So now we have one more example, so we can give it again to the PBE, which will come up with a new program. What will happen if the teacher would say yes? And let's say that this time these two abstract examples combined cover the entire input space. So at this point, we can tell safely that this program behaved exactly as the teacher wanted. Namely, the teacher has validated the program through the abstract membership query without even inspecting the low-level code. So let me demonstrate this back on our running example. So we had the input space and the program space. We were given an initial set of two input-output examples. We were looking for some program. But at this point, before returning it immediately, we will generate abstract examples. So if you recall of our wrong behavior of the program, what we will do, we will return this abstract example. And this abstract example says that for any string, such that the first one has at least two characters, the output looks as follows. This is the H, followed by the second letter of the person's first name, a space, and then the entire first name, comment, and so on. So the nice aspect of this abstract membership query is that it actually describes an infinite number of behavior. But this is much simpler than actually looking at the low-level program. So this should be much easier for the teacher to say, no, this is the wrong behavior, I don't want this. So at this point, she is likely to provide some counterexample. So now we have 3 examples, so we can look for a different program with our PBE synthesizer and say that this time we got to the correct program. So now we will return an abstract example that describes the correct program. So we have for any 3 strings, the output is hi, the person's first name, com, at, the meeting time, and so on. as before, we cover an infinite number of concrete input-output behavior. And this time, this is the correct behavior, so the teacher will accept this. But moreover, this time, this abstract example covers the entire input domain. So at this point, the teacher is guaranteed that the program satisfies her intent. Okay, so I want to go a bit to the technical part, and let me briefly describe how the LSEP works. So LSEP is our algorithm for learning abstract examples, and it stands for learning an SE pair. And it takes as input the program that it receives from the synthesizer and some concrete input. And what it is doing is it looks for the most general abstract example that generalizes this input and is consistent with the program that we have. How do we do this? So first, we define a partial order over the input sequence expressions. What LSEP will do is to traverse upward the Hasse diagram based on this partial order to look for the most general input sequence expression that is allowed. What do I mean by allowed? So a generalization is allowed or is okay if it has a corresponding output sequence expression that is consistent with the provided program. How do we know if there is such an output? So what we will do, we will construct it gradually from the list prefix and we'll try to extend it. So let's see an example. So here we have LSEP invoked on the wrong program that we have as a running example. And we start with Diane, and we know what the abstract example, we've already seen it. So what we want to do, we want to learn the abstract example that if we have the first string that has 2 characters, the output would be age, followed by the second character, and then followed by the entire string. Okay, so how do we do this? So first, conceptually, we have the input sequence expression, and at the bottom, we have the concrete input Diane, and at the topmost, we have any string, and we try to generalize this concrete input. So say that we start with this input sequence expression, that is, we want to replace D with D that can appear as many times as we want, from 0, 1, 2, whatever. Okay, so we are considering this input sequence expression, and we look for a corresponding output sequence expression. So we ask, is it correct that all outputs for these concretizations all start with an age? And this is correct. We know the correct behavior of this program, so we say yes. Okay, fine. So we continue to extend this prefix. And now we ask, is it correct that for all these inputs, the output second letter would be always I? And this time, this is incorrect, because we know the second letter is X1. So if we have D 2 times, the second letter won't be an I, it would be a D. So we say, okay, so this is incorrect. So we look for another option. And this time we ask, is it correct that for all concretization of this sequence expression, the second character would be I as many times as we had the D? And this is still incorrect, because if we have 2 Ds here, so the second letter would be a D and not an I. So we say, okay, so we can't do this also. And this time we don't have any other options to extend this prefix, so we say, okay, so this prefix is incorrect. Let's try another thing. So maybe we will try another prefix where age appears as many times as D, but this is also eliminated. And so we say, okay, so this input sequence expression is incorrect. We cannot generalize to it. But not only that, we also know that we can prune all its ancestors. Why? Read our paper. So we move on to another candidate. And this time we want to generalize D to any character. And this time the generalization will succeed. So we know that we can actually generalize to this input sequence expression. And what we will do, we will continue upwards this Hasse diagram and we'll only consider its ancestors. Okay, so up to this point, I showed you how can we guarantee exactness in PBE using these abstract membership queries. But what I want to show you now is that abstract membership queries can actually help the synthesis. In what way? Well, we could use the accepted abstract membership queries to expedite the convergence to the target program. Namely, if we go back to our framework, we can actually use the accepted abstract examples as part of the PBE. Because even if this program was incorrect, the user has confirmed this abstract example. This means that it has confirmed the input-output behavior of possibly an infinite number of examples. So maybe this would be beneficial for us. And what I want to exemplify now is that it is indeed beneficial. And to demonstrate this, I'll show you a bit of our empirical results. So we implemented this framework, and as a PBE, we integrated the most naive PBE, that is the one that constructs programs of increasing size, 0, 1, 2, etc., and returns the first one that is consistent with the examples. Okay. So in these benchmarks, we consider only programs over the bit vectors, but we can also consider string domain benchmarks. You can see this in our paper. Okay, so what were our benchmarks? So we compared to SIGIS, that, as I said before, it takes some examples, learns some program, and then it can actually ask, is this the correct program? So this might seem more powerful compared to our approach, because at a single question it can ask, is this the correct program? And it doesn't necessarily have to have all these abstract membership queries. And what I'll show you now is just a single benchmark that has 50 programs that were randomly chosen, but all of them, for all of them to learn them, SIGIS required at least 8 examples. Okay, so let's have a look at the results. So the first row shows how many concrete examples we required to learn the target program. And we see that we have an improvement of almost 40% in the number of examples. So the accepted examples actually helped us to converge faster to the target program. Another interesting row is how many abstract examples we needed before we could eliminate the candidate program and continue to the next one. So this number of 3 means that on average we had 2 accepted abstract examples that we could use to converge faster. At the bottom, what we see is on how many benchmarks we were better than SIGIS, namely we required fewer examples, on how many benchmarks we were equal, and how many benchmarks we were worse. And we have 2%, and this is 50 programs total, so this means 1 program. So this is it. So to sum up, we presented the notion of abstract membership queries, which provide a middle ground between membership and validation queries. And they provide a concise communication with the user while still enabling to cover the entire input space. We showed a new framework for PBE with exact learning, and we demonstrated that it can actually help to converge faster to the target program. So this is it. So thank you for your time, and I'd be happy to take questions now. Thank you.
Thank you, Dana. Thank you. So we do have 2 minutes for questions, so please do step forward to the microphone. All right, I will warm you up while people work up the courage to challenge what you have presented. So I'm particularly intrigued by the comparison with SIGIS. Can you elaborate a little bit on the experiments you've done there? So what kind of tools have you been looking at? How much of a grammatical restriction was on these benchmarks?
You mean the kinds of program that we consider?
Yes.
Okay, so the programs where we just took some constants, which could be either constant, and we just took all these bit vectors operators like shift and and so on. And then we just constructed this program, picked them somehow randomly. We then ran SIGIS, saw how many examples it needed, and if it needed more than 8 queries, then we took it for our benchmarks.
All right, okay. So how about, I mean, a key problem in many of the synthesis tools I've seen so far is that they required a very substantial restriction of the grammar, meaning thereby making this search space rather small. Can you comment on whether that's something you would need?
So you're referring to SIGUS.
Yes, exactly.
I assume that this would also be helpful to SIGUS. I don't know. I mean, it's not dependent on the DSL. Maybe we can benefit something else from this.
From the grammatical restriction?
From the DSL, but I think this is orthogonal to our approach.
Okay.
So I think this would also benefit.
Let's thank the speaker again.